Okay. Okay, let's get started. Turn in the homework assignment here. I'll give the next homework assignment on Monday, but make it online later today, right? Okay, so so far, we've been looking at more video compression algorithms, and we continue with that and go into MPEG 1 and MPEG 2, which are MPEG 2 at least is one of the most popular video compression algorithms, and it's used a lot. I mean, it's used in DVD and most of your cable TVs and stuff like that. The newer satellite systems use MPEG 4, but it's still a very popular compression scheme, right? And I think I mentioned this before, and Wikipedia had a interesting article that MPEG 2 is laden with patents, right? It's like they have like 640 patents with that's the essential component of it. So you may not see MPEG 2 compressors, right? So even if you try to do that for your projects, you'll find that there's like a restricted version of it, the one that goes for DVD. You can do it for DVD to make a DVD, but not a generic case of MPEG 2, right? So if you use Apple or something, and then you try to save the object as something, you can save it as MPEG 4, but not MPEG 2 because it has so many patents, right? And so the patents define, it gives it flexibility because it basically, they couldn't agree on how to do the compressor as one thing. So the compressor is sort of vague. It lets you choose whichever way you want to get the commercial competitive advantage you want. It's all proprietary. So the patents cover the basic components of MPEG, not the stuff that Adobe and all probably did for their own authoring tools, right? And that's the reality of it, and it's kind of unfortunate because we can't really play with it in the general sense. The standard defines a whole bunch of different profiles, and we only use one or two profiles because those are the stuff that somebody can get the patents for us, right? I keep always forgetting about that. So first we start with MPEG 1. So this is from the movie industry, and the H.264 was another standard, 261, and those things we looked at in the earlier lectures. It's another standard which came from the telephony, video conferencing kind of side, and this came from the TV side. So naturally, you'll see some of the differences that come from the TV broadcasting movie kind of fields rather than video chatting kind of stuff. One of the obvious things is the size is different. I mean, the size of what you want to send is different. So you have slightly different size. It's called the CIF, which is bigger than different than the CIF thing. And the different, like I said, each one has different profiles and different subcomponents of it. To confuse you, MPEG 1 audio layer 3 is really MP3. MP3 is not MPEG 3, right? There's MPEG 1, MPEG 2, MPEG 3. The standard they sort of wanted to form, and it kind of went away. Then they went out to MPEG 4. So MP3 is not MPEG 3, but MPEG 3 is MPEG 1 layer 3, right? And then the same you'll see with MPEG 4. There are, even though you say MPEG 4, it's a very broad term, and specific objects have specific meaning, right? The main thing that they introduced was the notion of the bidirectional motion compensation. I kind of mentioned that before, right? So remember, we had the notion of a I. Then we had a notion of a P, right, which is forward predicted from the prior I and P. So if you have an I can predict this P, and you can potentially have more P's, which can be predicted either like this, either this way or this way. So essentially, you have these things predicting the future, right? So this frame is predicted from here. So you need to get this frame, and that tells you what this frame should be. So you do the motion vectors and all those things, right? The notion of bidirectional comes in where there are some objects which don't really look, you can't really use the past to predict what the future is. The future actually predicts what the past was, right? And one example here is like if something is occluded, right? So if you're throwing a ball, and in the previous frame, the ball is not visible at all, So in the current frame, large part of the circle is not visible, but in the future frame, it's more visible. So I could translate back from here to here rather than from there to here, right? So the notion here is there are scenarios where, because of the occlusion and stuff, I may know more about what this frame is from the future frame than from a prior frame. The notion of bidirectional is I can create another form of another frame type, which can be predicted either from the past or from the future, right? And those are called B frame, right? And if you can do that, then you get, we will see how this really helps you in doing this stuff. And essentially, this works because you have motion, and there are things that you may see in the future that doesn't show in the past, right? Yeah.
What is MB on your slide?
Macro block, say, yeah. So the macro block containing that particular circle, the darkened one, right? So you can do the past, right? So why wouldn't we do this for H261? Remember the algorithm we were looking at in the last lecture, right? Or can you do this in H261? Or how would you do this, right? How would this work, right? I'm showing all these frames, but how would you think about implementing this stuff, right? Yeah.
Well, I guess with H261, I was trying to do streaming video, so you don't really have future frames to base your test frame.
Especially if you're doing audio video chat, right? So the only way you can get a future frame is either because you're operating on a static, some content like a movie, right? If you're not actually actively taking the movie right now, then you have the previous and the prior frame, previous and the next frame, right? And when you're doing video chat, you don't have the future frame, so you really can't do this stuff unless you save all the stuff, unless you save all the things, in which case it slows things down, right? So you can't really do this stuff in that scenario, right? So what is the complexity of doing this stuff in a loose fashion? What is involved with the positives are, that in this particular scenario, you can see the more of the circle in the future, right? So I can do more of the translation in the future, right? What's the negative of this? In all the compression, the negatives is always more computation, right? So I just say, just look in the future, right? Looking in the future, remember going back, you don't just look in the future, right? You have to define again the P matrix of how far you're going to look. And then you have to do this matching using whatever mechanism to figure out where the match is, right? So before, you would have taken these two frames and tried to figure out from this target, draw P around it and see where the match is. Now you have to do this for previous and the future, right? So the compression algorithm now becomes more complicated because you have to do twice the amount of work. I need to look in the back, I need to look in the future and see if it matches, right? And as you'll see, I can take it to an extreme level where I can have multiple frames, and I may want to do this P depends on this P and so on and so forth, right? There's no reason why you should just look at just the next frame or the previous frame. In fact, I can look at a whole bunch of frames and try to figure out if there's a match any time in the future, right? And for certain kind of videos, it may actually make sense. And it depends on the particular scenario that they're looking at. So it may so happen that this frame is the bad frame, but the next frame and the one after that has the stuff. So the more you look, you may be able to find the one which really helps you, which is maybe 10 frames out or something, and you can predict from those, right? So the computation cost increases a lot the more you have to go, and it's never clear that it's actually going to help you. So it depends on whatever you're trying to encode. So in some scenarios, looking in the future may help you. In some scenarios, it may not help you, right? For example, if you change the scenery, right? Change the scene from one to another one, right? It doesn't matter how far ahead you look because it's a different scene, so you may not see the stuff, right? And as these things don't really know, so it may have to do a lot of computation, right? But in the case of the way they were, the movies and all those things, it's not really a problem, because if it takes the movie industry to encode a movie, if it takes you 3 months to do it, you don't really care, because as long as you get the good compressed video, right? And so it's okay in that scenario. It's not really okay again in the case of video chat and stuff, because even if you could buffer all these things, the amount of computation required may be really bad, right? But potentially, it can actually get you good compression. So essentially, for every frame, you do 2 of these things. You look at the previous one and the next one. You figure out what the matching vector is. If you only get one vector, either the past or the future, then you're good. If you get both of them to match, then you find the average, and then you encode that, right? So again, you do the same thing like before, but the differencing, you take the current frame, predict where it went in the past, predict where it went in the future, and then you get those 2 blocks, average it, and then see the difference between that and the current frame, right? So the idea here is, I have 3 frames, right? So this particular block, the motion vector was here. And let's say the motion vector was this, and then the motion vector was something different here, the mode, whatever, right? So what you do is you apply this motion vector on this block, right? That says if you translate from here to here, you get this one. You apply this motion vector on this block. That means if you apply this, you get this stuff, right? And then you average those 2 resulting ones, and then find the difference between the averaged image from doing this motion with this one, and that's the difference that you need to encode, right? And hopefully the difference will be small, so you get more compression. Does that make sense? Right? And if you only find 1 or 2, then one or the other, then it goes back to how it was before. So essentially, the way you would encode right now is you have a certain number of I frames, certain number of B frames, certain number of P frames. And you may decide this a priori how many frames you want, or complicated encoders may do this on the fly. So essentially, again, you have the notion of I frame. You need I frame for the whole thing to start, right? You never predict anything beyond the I frame. The I frame defines the boundaries of the stuff. You need the P frame to predict to figure out what the B frame is. So even though this particular screen has I, B, BP kind of thing, you need to transmit it at this level, right? I, and then this P, and then this B, and so on, because you cannot figure out what, for example, this frame is till you have this P, because this B is predicted from this I and this P, right? So I need to transmit it as this I first. I need to wait for this I and this P before I can decode this one, right? So I may either have to transmit it like this, or I won't be able to play this frame till I get this one, right? That makes sense? Because we are worried about transmitting the stuff, so I need to make sure that these things are received before you can do the stuff, right? So what this means is I can't just randomly jump into any of this stuff. I can't just I can't see what this frame is, right? How do I get? So if I do a rewind, right, of this particular video, and I want to see what this frame is, right? How would I do that? I only care about this frame, right? How would my rewinding go? Yeah.
Wouldn't you have to get? I mean, if you're rewinded and you want to see that particular frame, you have to get the iframe before it.
Yeah.
And the P and B, all of ones.
Yeah.
A good group of frames.
Yeah. So exactly, you have to get this whole group to figure out what's going on, right? And so there's a notion of a group of pictures, right? So these pictures are sort of a group, and you can sort of jump back into the group, but if you want to go inside, you have to do all this computation to compute that, right? So if you want to go into any of those frames, you go back to a group of pictures, a certain number of pictures, and then you start from there, right? And as you would expect, the group of pictures have to start with the I frame, because without I frame, you can't do anything. So that defines the stuff, right? That defines how you do these things. So you sort of have some complexity on the receiving end too, because the receiving end just cannot go anywhere it wants, but that's a price you're willing to pay. And then we use our usual quantization stuff. We drop certain frames, certain components more than anything else because we know the iframe has all the detail, right? Iframe has all the detail that are used by the subsequent ones. So you want to maybe have a different way of encoding the iframe, different way of doing the p frame, different way of doing the b frame. We didn't do that for H.261. Remember that H.261, we scaled all the frequency components with one constant values. And here they introduced the notion of sort of like what you have with JPEG. Different stuff for the I frame, different stuff for the P frame, different stuff for the B frame, because again, this is sort of what you would expect to do, right? Yeah?
So the difference between the P and the B frame is the information in the B frame is not used to predict any other frames. Is that correct?
Well, B can be used to predict future B frames.
What's the difference between P and B?
P is only forward predicted. So this P is predicted from the prior I and P, whereas the B could be any of the prior or the future ones, right? So in fact, P is a degenerate case of B frame. But the reason why you want to keep them separate is because then you can apply different algorithms to those, right? Usually the assumption is B frame can have the most aggressive compression and P would have less aggressive compression. I would have even least amount of aggressive compression, right? The way we control the aggressive compression is through the quantization table. So now we have different quantization table for all these different components, right? So generally speaking, there is no reason why P should be smaller than P, B should be smaller than P or I, but we kind of make an assumption that I is more important, P is next important, and B is not important, and we apply different quantization, right? And for the DCT components, you still do the divide by 8. But for the AC components, now we have different matrices. I didn't bother to bring print the matrix. It's in the book, and essentially you will see that different frames get different levels of aggressiveness noted by the size of the number, right? The larger the number, the more components you drop, the more zeros you get, right? And so even though there's no reason why there should be the case, we decide to do that. We get more compression. So in this particular case, right, the compression factor you get for the iframe size is about 18 kilobytes, and P is 6 and B is 2.5. The compression ratios you get are about 7:1 for the I, 20:1 for P, and B is 50:1, right? And again, there's nothing inherently bad. I mean, something about the B frame why you should compress more than P frame. It's just that we use a different quantization to drop more of the components. So if you average this out, given a certain ratio of I, P, and B, you would get, say, 27:1, right, in this particular example, right? How would you choose a number of B frames? How would you choose this thing? So now we need a combination of I, P, and B, right? In the last lecture, we kind of looked at how you might choose the I and P, right? The reason is, you want a certain number of I's so that you can have some sort of redundancy, because if you lose I frame, you lose a whole bunch of stuff, right? Going beyond that, how would you choose the P and B? Is there inherently any reason why you would choose a certain number of P and B? Or is there a practical reason, given that you're dropping lots of the quality on the B frame, why you would want to do something, right? What would happen if you have lots of B frames, right? Yeah.
You'd have to transmit a lot of the video out of order if you had a lot of B frames, because you'd have to have everything after that depended on 2, instead of just being, if it was all P, you could just go in this is straight.
Oh yeah, that's the excellent point too, because if you have lots of B, then you have to go way into the future, transmit those across, right? You need to have all this stuff in memory, and you also, since you're dropping a lot of the components, they are not as good quality as the P frame, right? So at some point, if you have too many Bs, then your video will look bad, right? So you choose something. So again, this is some parameter that's left up to the encoder. So if you're a movie studio, then you have to decide how much of I's and how much of P's and how much of B's you want, right? And given certain stuff, you may get different quality, right? You may not have noticed, right? But if you look at, this is not DVD. This is not the DVD encoding. That's MPEG 2, right? But even in DVD, right? When you watch your DVD movies, many players have some functionality to show you what the bitrate that's encoded, right? How many of you seen the bitrate encoding stuff? So few of you have seen it, right? And you may notice that there are some movies which have lot higher bitrate than there are others which lot fewer, right? Like the mega releases tend to have more bit rates than the ones which go directly to the $2 bin kind of stuff. And essentially that's what you're trying to do, right? So if you have more data rate, then you're trying to get more quality and stuff. DVD kind of restricts the upper bound to be 10 megabits per second. But certain encodings will be close to the 10, but certain will be close to like 4 or 3 or something like that. And you can see the quality difference in terms of fast forward, stop, and stuff like that, right? So next time you watch a movie, try to look at those things. Usually you can't tell exactly, but you can see these things. And you can also see when things are changing a lot, when there's like lots of movement, the bandwidth will go high, and when nothing is happening, even on the good quality ones, it'll drop back down, right? And there are other things you can do, and we'll see those. In terms of actually, when you do these real things, you don't have to count the whole frame as one thing. Like so far, I've been talking about the whole frame having one quantization table, the whole iframe having one quantization table and stuff. And on MPEG 2, you don't have to do that. You can choose the quantization table for different areas, and the more you can do that, the more better it'll look, right? I thought I had some characters here. So I don't know what happened. So I'll try to see what happened. So if you look at the FAQ for MPEG, right? Everybody hates the B frames, right? Because B frames depend on. Did it show up on the handout? Okay, I don't know what happened here, right? So the B frames people tend to hate because it increases the computational complexity, right? So and it increases the memory complexity. I need to keep all these frames. It delays what I have to do. I need to keep all these frames to calculate what it is, right? It affects the order in which I can transmit and stuff like that. So a lot of folks, especially the cable industry, was not a big fan of B frames, because the more you have to define, the more you have to do this stuff, the more frames you have to remember, right? And the memory on the cards tend to be small, on the cable boxes tend to be small, right? So if you remember, even a few years back, when you buy graphics cards, right, 8 megabyte graphic card was not, was still sort of like the high end, right? People used to have 4 megabytes, 2 megabyte graphics card and stuff. And essentially, these frames have to be stored somewhere. So if you're having a cable box, memory was still considered to be expensive, so they don't like to have all this stuff. So they severely restrict how many B frames they would like to use, just because they don't want to. So here the complexity is the more B frames I can send, I'm using less bandwidth, but I'm pushing the complexity, in terms of memory and computational to the receiver end. In case of the cable TV vendors, they don't particularly care about the bandwidth on the transmission line, so they may not use much of the B link, right? So we haven't looked at how cable TV works. So why wouldn't cable TV vendors care about the bandwidth usage? I said if you don't really care about the bandwidth usage, you don't really have to use that much of a B, right? Or if it makes it simpler, you can think of DVD, right? Why would a DVD producer not care about bandwidth? Think of how you have what it means to say bandwidth for a DVD, right? Okay.
I mean, you just have it's all inside your player, so you don't have to worry about getting over the network or anything.
Yeah, so if you have a DVD disc, right, as long as you can fit your movie into it. So if you have like a 4-hour movie and you're trying to put it into one DVD, you have to worry about all the stuff, right? But if you have 1-hour movie, and if you do the simple math that the max can be 10 megabits per second and all those things, so if you have the bandwidth allowed for you, I mean available to you, there's not really much motivation for you to go out of your way to do this stuff, right? And similarly for the cable industry, when they used to have like a certain, 100 cables coming into your house, so they have enough bandwidth to send certain amount of stuff to you, there's not a whole lot of reason to worry about it, because as long as you have the bandwidth, you don't worry about it, right? But as you move into the change the technology where cable industry can send however much you want, and they have to do smart stuff to get you better stuff, right? And we'll see a little bit of that with the IPTV stuff, right? The IPTV, which is one of the things I started off by saying, it's the digital TV coming to you through your phone lines, right? I think AT&T sells it as UVerse, at least in the Granger area, right? So they only get 20 megabits to your house, right? 120 megabits to your house, and they advertise they can send like 300, 400 channels to you, and the way they do that is through compression and sending these different things, playing different games. Then you worry about this stuff. But in the vanilla cable industry, they probably didn't have to worry about it because the number of channels was enough for what they were trying to do, so they didn't have to bother with some of these things, right? There are other differences that you may have noticed it, especially when you're looking at it in MPEG 2 or MPEG 4, right? How many of you have played with video in iTunes and podcasts and stuff like that, right? How many of you have like a iPhone or iPod video, something like that? And have you tried to encode something for to put on the thing, right? Have you tried to put your own video onto this stuff? So if you try to, you can try that for the project one, right? So if you try to do the stuff, if you look at the specifications of what goes into the iPod player, the specification won't be in terms of you should have a 640 by 480 video, right? It will be in the terms of you can have up to 800 macro blocks, right? I'm just making up 800. But the specification will be the iPod player can play 800 macro blocks, right? And you can choose how you do the stuff, right? And you begin to see some of that coming in here. So the amount of video that you can encode depends not on the dimensions but on other factors, because there's all the complexities being added. So you have a size limitation of what the x-axis and y-axis should be, but you also have the notion of number of macro blocks. So you can play games to make this stuff. So within a certain stream, you can change some of this stuff to have a bigger or smaller image, right? So it depends on how much computation that essentially which translates to the macro blocks, and not necessarily on the size, right? Whereas when you're talking about H.261, it was only the image size, not the number of macro blocks. And more complex things, all these things come into play. The frame rate, so essentially the frame rate, all they're saying is you should be able to say, operate on, let's say 800 megabucks per second, right? 800 macro blocks per second, right? So if you have more frames per second, then you'll have less macro blocks. If you have less frames per second, you can have more macro blocks and so on and so forth. So you can play with this stuff to get the compressor is not defined by one thing. You can change this stuff, right? And especially when you're talking about a movie which is 24 frames per second, you tend to have more frames, less frames. That means you can have more quality, because you can send more of other stuff, right? The other major difference is the notion of a slice, which you'll see it's taken all the way to MPEG 2 and so on and so forth. So the idea here is within a particular frame, remember that we have the notion of the blocks, right? We have a notion of a block. Then we have a notion of a macro block, which is a collection of blocks, right? Then in the H.261, we had the notion of a group of blocks, right? where it's a group of the macro blocks. And here we call it slice. The idea here is I can define, so let's say this, let's ignore the block size, right? So I have a macro blocks, right? I can define all these macro blocks to be part of a slice, right? So I can treat them separately as one entity, right? The only restriction is everything has to start from here, and it has, I mean, all the macro blocks have to be part of some slice, right? So otherwise you won't have the whole image. So essentially you take this frame, you split them up into these slices if you chose, right? So I can say these ones are all part of one slice, and these ones are all part of another slice, right? The reason why I want to do this is then MPEG allows you to choose different quantization table for different ones, right? So essentially it lets you take your single frame and treat parts of it as if they're different videos, right? So I can aggressively compress this and not so aggressively compress these, right? It doesn't specify how I should choose this or when I would know what to do, right? But if I knew what to do, if I knew what I'm encoding, I could potentially specify what are all part of the slice. Then I can potentially have different ways of encoding. So I can be more aggressive here and less aggressive here, right? So can you think of a reason why you would want something like this? Think of some sort of video, and where might you use something like this? Think of this video, right? Like, let's say that this video is taking off this board, right? Would you need to compress all the frames equally well, or can you think of a reason why you would want to compress certain parts more than the other? Right? So let's say the video can take all the way from the ceiling to here, right? And let's say it can take all the way, all this board, it can take all this stuff, right? Yeah.
You could compress images of a blank chalkboard or the blank white wall very aggressively.
Yeah.
If there was details on the chalkboard, or if you were moving a lot, you wouldn't be able to do that.
Yeah, so in fact, yeah, that's exactly it, right? So like this part, right, we are hoping that I don't go up and right there. In that case, I can, so I can do this for a group of pictures, right? We haven't talked about that. So I can say a group of pictures, so I can say the first 1 minute, I never write anything on the top. So for the first 1 minute, I can define a slice, which is all the macro blocks over there, and compress it so aggressively that you can barely see anything, right? I can basically drop everything. All you see is like a black box, right? Or like, so basically the DC component up there. And then I can divert the information that I would have sent there down here, right? So I can use a less aggressive quantization table for something over here, especially the quantization table for the writing stuff, right? Because all this JPEG and all those stuff don't really like high frequency components like writing, right? Writing is a high frequency component because there's an abrupt change from the black to this white and then goes on, right? So they don't particularly like this stuff. You need to have good quality. So I can direct the quality where I want, right? So if you think of like looking at a football game or something, so essentially the sky can look blue. I don't think anybody would complain. People would complain if you can't see the ball or if you can't see something happening over there, right? So the notion of a slice gives you more power than group of blocks, where if you define the group of blocks as like certain static stuff, then I have no control over what I can do this stuff. But if I give me the privilege to do the slides, so for example, I can define a slice sort of like this, and where the different colors are from different slices. So then I can use different quantization on each of those, right? And so the other thing, it's good for error recovery because if I have to lose some component, if I lose like this particular slice, right, then the image will sort of look jagged, but the rest of the image can still be there. So I'm kind of decomposing the picture into different images, right? And we'll see more of this notion coming up when we'll see in the layered encoding in this chapter, and more of a notion of MDC and all coming up in the future, where if you're trying to stream these things, you worry about this stuff. You want to send as much quality to certain parts of the image, but you also want error recovery, and you also want to be incrementally adding this stuff, and especially when you're talking about IPTV and all those things, where if you have good quality signal, if you're watching it on your laptop or something, and you're something streaming, you would like the quality to improve and go off in some nice fashion, right? So you want all this control. So slice is one of the stepping functions toward the stuff, and more complex ones have more complex stuff, right? There's nothing complex about what happens here. All you have to say is, I'm defining these particular blocks to be a slice, and I have to define a quantization table for this particular slice, and that's it. And essentially, if I'm decoding or operating on that particular stuff, I need that quantization table. So the only stuff is I need to have one quantization tab for here, maybe another one for here, and so on, right? The power is in how to use that, right? So how would you use this? So for your project, right? Do you think this will be an easy thing to use or hard thing to use? Defining this notion of a slice and defining quantization for different components, right? How might you use this stuff? And I haven't thought about it for a while, but how would you choose this power to send certain parts of the image in good quality, certain parts in bad quality? Would you do this on your camcorder? Would you do this on a post-processing tool? Yeah.
Would iMovie do this type of thing when you export your movie for YouTube?
So how? No, it doesn't. But how would iMovie do this, right? How could iMovie do this? What would iMovie need to know to do this, right?
You have to know what's important.
Exactly, right? And that is a very important, okay, that's a very important concept that we'll see, right? If I can figure out what is important in a screen, in an image, I can do a whole lot of stuff. So when you go into MPEG 4 and MPEG 7 and stuff, if I knew what is important in a scene, I can do all these things essentially. So whatever you did in H.261 is practically what we're using when you go to the higher stuff, right? The more complex algorithms let you direct the techniques we learned, like quantization, all those things, differently on different parts, right? And for those to happen, you have to have a notion of what is important. So if some component is important, you want to give it more, and some component is less, you want to give it less, right? We didn't introduce anything new here. We just said we use different quantization table, and we know that quantization table is the one which gives you more compression because it zeroes out the high frequency components, right? And finding out what is important in a scene is an extremely active area of research, right? Trying to figure out what is important and stuff. You may see variants of that when you see the new camcorders, right? So new camcorders have a face recognition algorithm, which you might have seen the advertisements, right? They recognize where the face is. They don't go into all the detail. They don't say, if you recognize a face, we're going to mark a slice around it, right? But essentially, that's what you would like to do, right? So if I'm taking a picture, if you can detect where the face is, then it can compress those components less. And if it can sort of detect where the blue sky is, it can compress those away, right? Because assuming that people don't really care about the sky, care about the faces, right? Because consumers, that's what they tend to use kind of stuff, right? But it's a very, very hard problem because if you want to do this right, if you want to do this manually, right? This particular case of this lecture is sort of the boring case, right? Because the camera is kind of stuck, and I'm kind of stuck. The board is not moving, and it's all good, right? But in real life, things move, things change, and all those things. So what you really want is, I want to look at each frame by frame, or some sort of group of frames, and I want to do editing, right? And this is essentially called nonlinear editing, right? iMovie does help you with that. So you have all the frames, then you can somehow mark these things, right? So if you look at the new iMovie, it lets you look at the different frames and try to do something with those. You can actually mark certain areas and then make them brighter and stuff like that, right? If you look at those kind of operations, it's extremely painful because every second is actually 30 frames, right? So you have 30 of those frames, and unless you have like tons of time or tons of money given to you, right? Most of the time you don't want to sit up, and even if iMovie could do that, even if it gave you the power, right? Many of us have enough stuff in life that we don't want to look at 30 frames and mark all these are important or all these are not important, right? Which is not true for if you're making Lord of the Rings DVD or something. So that's one of the reasons why it takes. So when you see it from the movie to the DVD, it's a big effort to make it into a DVD because they're trying to do all the stuff, right? You may have seen in the popular press that for the Star Wars DVD to come, right? The director did not want to let it go till he was happy with the quality of the first one, right? That's because they didn't actually take the movie, put a camera in front of it, and then encode everything, right? Because it only gets you so far. So they had to kind of say where to get the quality, because you are kind of stuck with the certain amount of quality, because you have 10 megabits per second. You can do a bad job by giving equal quality for the whole scene, but you can do a good job by saying this part is important, this part is not important. And if you can do it automatically, that's the holy grail, but it tends to be extremely hard because of automatic stuff. So if you have one of those cameras which recognize faces, right? It'll work really good if you do what you're supposed to do. If you're taking a picture of a child, and they probably do some studies to figure out what people take, right? So let's assume they find that normal consumers take pictures of kids, right? So they assume what's the size. Very rarely do people put a child in a mountain like a mile away and try to take videos, right? So they can make all these assumptions and they do all the stuff, right? So you ever wonder what happens if you violate all those stuff, right? If you take something which is not, they don't expect you to take, right? Then it's going to make choices which may or may not work out for you, right? And it's a big problem because whoever can solve that, remember, all these things are multi-billion, trillion-dollar, big industry. So so even though MPEG-2 has been around for a long time, the research in terms of what to do with that is not done because the MPEG-2 gives you the basis of creating these slices, but what to do with that, it's still an open problem that you continue to work on it, right? And yeah.
So you said the upper limit for the bitrate on DVDs is 10 megabits per
Yeah.
second. What's the upper limit on like the Blu-ray?
I don't know I know Blu-ray is MPEG-2, right? Blu-ray was not MPEG-4, but there's a variant of Blu-ray which can do MPEG-4 or AVC. I don't know actually what the bit rate is, right? But it's more complex than that because it also depends on the size and all those things, right? Yeah, I was kind of surprised that Blu-ray did not go with MPEG-4 and they went with MPEG-2, right? It has to do with cost, right? Because one of the things you realize is all these operations, because we do all these blocks and stuff, is easily parallelizable, right? Because essentially all these operations are in little blocks, right? So if I can get this block and I can do this block, I can implement all those things in hardware, like the MAD and all those things. I can do it in hardware, right? So many of these things can be done in hardware. Many of these things are easily parallelizable, and many of these things are integer based for a reason because it's easy to implement, right? So you have MPEG chips, right, where you don't want an MPEG chip where you give it a video and out comes a video, right? That's one thing you may want for low end stuff, but you want an MPEG encoder where you can manipulate the slices and still help doing the stuff, right? So a lot of effort goes into building these MPEG chips. There are a lot of issues of what sort of works, what doesn't work, right? And then once you have those things, you want volume, right? You want something that especially for the DVD players, they're probably making like billions of these, right? So when they go for Blu-ray, they have a choice of going between MPEG-2 and MPEG-4, and they probably chose MPEG-2 because that cuts the cost on what they get, right? So at least I know Dish Network went to MPEG-4, right? The satellite player. How many of you use Dish Network? Right? They went from MPEG-2 to MPEG-4, right? And so the cost of upgrading is they have to upgrade the satellite. one-time cost. I mean, they had to send a new satellite and all those things, right? But they also have to upgrade all their customer boxes, right? So they took a big hit, and I wish Blu-ray would have waited a little bit longer to get this stuff, but there was this other political fight between Blu-ray and HD DVD, so they went with the MPEG 2. So yeah, pretty much MPEG 2 is like sort of the standard for everything except download services, right? So the other thing is, again, we're still in MPEG 1. MPEG 1 lets you do half pixel for motion prediction through bilinear interpolation, and it also increases the amount of area that you can look from 15 pixels all the way to 1024 pixels, right? And most of the time the point is mute because the image may not be that big, right? So if you're operating on the 300 by 200 or so things, it doesn't matter. But essentially, it allows you to, for motion vector prediction, look throughout at a much larger size, right? Is that a good thing? Remember the p-value for motion vector prediction, right? Is having a larger area a good thing or a bad thing? I think, yeah.
It would cost more computational time to compress it.
Yeah, it's not clear, right? Yeah, it's more computation because now you have to check a lot bigger area. So it may be good, it may be bad, but it's there, right? Sometimes it may not even be practical because the image is smaller than what you can do, but the standard does let you do the stuff. So again, the thing I mentioned, they group a bunch of pictures into a notion of a group of pictures. So when you do a fast forward or rewind, it has to go to a next group of picture and then start decoding from where it is, right? And you may notice some of the stuff when you see in a DVD, it never does go back very smoothly, right? If you play a DVD, there's the issue of the disk having to spin back to get to wherever it is. But these things are not very smooth. You can't go back and forward smoothly because you have to go back to the group of picture and come forward, right? Sometimes you may notice it, but sometimes most of the time you won't. So that's the MPEG 1, right? Actually, MPEG 1 was, I didn't mention that, was used in VCDs, right? VCDs, the video CDs, they never caught on in the US, but they were really big in Asia, right? So essentially, you wanted to store a whole movie into a CD, around 600, 700 megabytes. So the compression is more aggressive. It doesn't let you store bigger frames because you only have 600 megabytes. What caught on more in the US was the DVD. DVD essentially had 7 gigabytes or so, depending on the dual layer stuff. So once you have 7 gigabytes, then you can do a lot of stuff, right? For example, now you don't have to worry about the bandwidth. I can have bandwidth to be higher, 4 megabits to 10 megabits per second because I have a larger disk to store. And so now I can store bigger frames. Now I can store better quality audio. Now I can store better quality video. And that also means that I get lots of variants, right? Lots of profiles and stuff. So it defines 7 profiles, including simple, main, SNR scalable, spatially scalable, high, 4:2:2, and multi-view, right? Your iMovie only does simple and main, right? It doesn't do any of the other profiles. And like again, I said, those are the ones you need for your DVD, right? Your DVD, so it does MPEG 2, but only certain profiles. It only does simple and main, and the image size can only be these, right? And the video peak megabits can only be 9.8. The total can only be 10.08. Minimum can only be 300 kbps. So it's a restricted form of MPEG 2. And since that's all you are expected to do with the sort of Mac, your Mac can only operate on the simple and main profile, right? The other profiles can get you, it's suited for different kind of setup, right? For example, the multi-view is designed for picture-in-picture kind of stuff, and those are not taken care because the higher profile means that you need to have a way to specify all the profile information. And simple and main can take any image and operate on them. So that's what you operate on. And the book gives you a table of the different profiles and what is supported for the different sizes, and for the main profile, what the different size of the images are, right? It's just for You can use them for just checking out. So essentially, it can start an image as small as 352 by 288. It can go up to 1920 by 1152. And I think the bandwidth can be 80 megabits per second and so on, right? So MPEG 2 is sort of the standard we use. MPEG 4 is more of a newer one. I'll continue with this on the next lecture.